Hey guys, what's up again? Hope you had a good Easter. Our first tutorial back after the break. Sorry about the lighting in this room. Kind of shit because it's a sunny day today. So for most of the tutorial, I'm probably just going to look like a black blob in the lower left corner. But that's fine. Now, a few things I want to say after correcting most of the work. And you guys should really be doing the homework by yourself. Okay? I understand you're in first year, it's online, it's a hard module, you wanna, you know, you wanna get a good grade. But honestly, it looks really bad when I'm correcting a problem set and there's 10 different answers, or I mean, there's 10 answers that are all the same, and they're all wrong in the same way, you know. So, I really would recommend, like, if you don't write down something on your homework, if you don't understand this, okay? Another thing, don't just go to clouds and solutions and copy them, because solutions aren't proper solutions. They're, in some places, they're just guides to the solution. They're hinting at what you need to do, quite obviously. So don't just copy him word for word either. Bit late in the year to be saying this, but this applies in all other modules too. Attempt the homework by yourself. Write down what you understand. If you don't understand something, don't write it down, and then your tutor or your lecturer will be able to help you. They'll see what people aren't getting. It's hard for me to understand what people aren't getting because everyone's copying each other. And this is fine in first year, do you know what I mean? But if you go into second, third year, fourth year, it's just not gonna fly anymore. The other thing I would say is attempt the tutorial by yourself. Don't just watch my video and skip 5 seconds and you watch it. Sit down with a piece of paper while you're watching and try and stay 2 to 3 lines of calculations ahead of me. Try and predict what I'm gonna do. And if you get it wrong, it doesn't matter, because you'll see in the video 2 minutes later that you're wrong. You'll be able to go back and you'll understand it better, and you'll see what you did wrong and what you thought was not actually true. And this will help you in every math module. Right? I'm not just talking about linear algebra. If you have more math modules, the best way to get a high grade is to just practice more than everyone else. Because when the exam comes around, you will be prepared, right? You'll know what you've messed up before, and you'll be able to correct for it. Okay, so that's my college advice over. If we look at the poll's still up at the moment, by the way. Thanks to the 4 other people who voted since the last tutorial. But if someone else wants to be the tiebreaker here, right, to decide what we're going to do in the last week and sort of a fun tutorial, go vote here. Link in the description as always. And that being said, I guess we should crack on with the tutorial. This sheet is a long one, okay? Lots of parts, lots of different things happening, mostly about determinants. So let's get on with it. So we're given a matrix A here. We're going to be seeing it quite a lot. And the first part just wants us to compute the cofactors along the first row. Okay? So I'm going to write the formula for anyone who hadn't seen it from lecture notes or just wants it written down. The cofactor along ij is going to be -1 to the power of I plus j times the determinant of aij. Okay? And aij is the submatrix that we get when we delete the ith row and the jth column. Now I know this formula looks really abstract when you first see it. It's not actually. Right? You're about to see. So I'm going to write down A here, just so I can scribble on it and show you visually how I do this. here to A. We're going to start with C11. We know when we plug this in, we get minus 1 to the 1 plus 1 here, definitely. And then we're going to get the determinant of A11. Now, what is A11? A11 means go to the first row and the first column, right? So this entry right here, delete its column and its row, and then take the determinant of what's left. Okay, because this here is the submatrix, right? And when I take the determinant, I'm taking the subdeterminant. Just some terminology. And if we do that, okay, just delete this for later. Filling this in, minus 1 to the 1 plus 1 is minus 1 squared. And now I'm going to get the determinant of A11. It's going to be this determinant. So I do 1 times 1 minus 1 times 0. Okay, and this is the shape I always think of when I'm taking a 2 by 2 determinant. Like that. 1 times 1 minus 1 times 0. Kind of fish shape. Okay? So that's going to be 1 times 1 minus 1 times 0. Precisely. Minus 1 squared, any number squared into a positive number, so that just gives us 1. And inside this bracket we have 1 minus 0. So the thing comes out at the end to just be 1. So we've got the B11 right there. Not too bad. I mean, immediately running out of space. You know, like, life never changes. So C12 is going to be very much the same thing. So I go to the, well, first thing I should write down is this is going to be minus 1 to the 1 plus 2. And now the determinant of A12, which means go to 1, 2, right, first row, second column, right here. Delete row and column, and then take the determinant of the remaining guy. Okay, so that's going to be 0 times 1 minus 1 times 1. Alright, not too bad. So the first term here is minus 1 cubed. Minus 1 cubed is minus 1. Inside the bracket here we have a 0 minus 1. So we have a minus 1 there. And these are going to multiply to give us plus 1. So I get C12 with plus 1. Alright. C13. Again, minus 1 to the 1 plus 3. And if we ignore the green now, I go to the first row, third column, I delete the row and the column here, and I have to take the determinant of what's left. So this guy minus this guy. Okay, sorry for all the scribbling. I know it's missing, but I think it's better for me to show you how I actually scribble. There's nothing wrong with scribbling on your matrix, right? There's nothing wrong when you're multiplying a matrix to literally draw the line and think about it like that. Okay? You never get marked down for being messy. You only get marked down for not understanding. So we do 0 times 0 here minus 1 times 1. Over here, this is minus 1 to the power of 4. Now you can think of minus 1 to the power of 4 and minus 1 squared times minus 1 squared, but they're both plus 1. So I actually get a plus 1 out here. Inside I get 0 minus 1. So I took the minus 1 here. So at the very end I get minus 1, like that. Okay, so we've computed all the cofactors, C11, C12, and C13 along the first row. And so for part B, we want to use the cofactor vector to compute the determinant of A. Well, our cofactor vector, C11, C12, C13, is going to be 1, 1, minus 1. And we know that the determinant of A is going to be the alright, in green, not math. The determinant of A is always going to be the ith row slash column dotted with the cofactor vector along the same row slash column. Row slash column. Okay. What I mean by dotted here, you take the dot product of them. Okay. So in particular, what we have is the cofactor vector of the first row. Okay. So the determinant of A is going to be the first row dotted with the cofactor vector along the first row. So let's get the first row of A. First row of A is 1, 2, 1. So it's going to be 1, 2, 1 dotted with the cofactor vector 1, 1. Okay. Don't get confused by switching between writing vector horizontally and writing them vertically. It makes very little difference. As long as you know, right, and that you explain that this is the vector, then it doesn't matter if you write it like this or like this. So if we calculate this, that means add together just the direct multiplication of each row here. So it's going to be 1 times 1 plus 2 times 1 plus 1 times minus 1. 1 plus 2 minus 1 comes out to be 2. And it's our answer. So the determinant of A is 2. And now for part C, we want to show that the cofactor vector is orthogonal to the second and third rows of A. Alright, I'm going to rewrite A. So we remember it. 1, 2, 1, 0, 1, 1, 1, 0, 1. Our cofactor vector, which we're going to call C1 on the front row, came out to be 1, 1, minus 1. Now, if I take the dot product with the second row, that's going to be 0, 1, 1 dotted with 1, 1, minus 1. And so I just do 0 times 1 plus 1 times 1 plus 1 times minus 1. And you can see this is going to be 0 here, plus 1 here, minus 1 here, comes out to be 0. Okay? Now the dot product, alright, let's explain ourselves now. This isn't good enough. Let's explain that the dot product of the cofactor vector and the second row is 0, therefore they are orthogonal. Alright, make sure you explain stuff like this. Alright, if I left this out, then the question would be asking to show that they're orthogonal, and then I've just taken a dot product and made it here. You know? can explain it beforehand. Alright, you can write here, if they're orthogonal, then the dot product must be 0. Let's show them, and then just do what I did. Right? There's lots of different ways to write down solutions to things in math. In particular, there ain't no one right way to do it, which is why there's no need for you to be copying clouds and hit solutions. You can write your own solutions in the way that you understand it, instead of trying to understand how cloud is working through the question. So that's the second row, third row, again, running out of space. We should be fine though. So third row, 1, 0, 1. 1, 0, 1. Dotted with 1, 1, minus 1. Should be able to see, get 1 times 1 plus 0 times 1 plus 1 times minus 1. Then I got a 1 here, a minus 1 here, and a 0 here, so that'll add up all to 0. And same reasoning as beforehand, dot product is 0, therefore these guys are orthogonal. Okay? Not bad. Or actually, something I should say here. This is always true. Okay? If I get the cofactor vector along the first row, then when I dot that with the first row, I get the determinant. And if I dot it with any other row other than the first row, I'll always get 0. They'll always be orthogonal. The reason why is a little bit more out there, right? It's not intuitive, given what we know about linear algebra so far, but it's true. Okay. So if I take the cofactor vector along the ith row, then if I dot it with the ith row, I'll get the determinant, and if I dot it with any other row other than the ith row, I'll get 0. Okay. So part D now is asking us to compute the dot product of R1 with R2 cross R3. Okay. I'll write A again. Just know we're not moving up and down a lot, because scrolling on this thing for me isn't great. I always accidentally zoom out or rotate the entire screen or something stupid. So this is our thing A. We want the dot product of R1 with R2 cross R3. Okay, so R2 cross R3 first. I'm going to calculate this first, because here R2 cross R3 in bracket. We know we always do brackets first. So, how do you do the cross product? You should have seen it in lecture now. It involves determinants. Okay? It really does. And it's kind of hard to see why, but R2 cross R3 is going to be equal to, do it now, 0, 1, 1 cross 1, 0, 1, which is going to be equal to, and this is the formula that most people use. Alright, it's the easiest way to write it down. It's going to be the determinant of this matrix, where in the first row we put I vector, J vector, K vector, 0, 1, 1, we're writing this row and the column, and then 1, 0, 1, writing this row and the column. And it matters the order you do this in. So if I had R3 cross R2, then these two would be switched, and the answer would actually be different. So it's important you keep the order here. Now, what do I mean by I vector, J vector, and K vector? You don't need to put this vector symbol on top. This is just something I picked up from physics, because that's what we do. I, J, and K are the Bateman vector, and because of that, you might prefer to write the E1, E2, E3. But this notation is a little bit slippy. Because of course, E1, E2, and E3 are all vectors. So how am I taking the determinant of a matrix with vectors inside of it? We just have to be careful, okay? But just remember, once you've computed the determinant, right, and you have the I and the J and the K and all multiplied out, you can then switch in for E1, E2, and E3 to get the final answer. Okay? Let's do that. Let's find the determinant of this. Well, what we know is that we found the cofactor along the front row before. Okay? That's black. So if I delete the front row and front column of I here, well, actually, this just looks like C11, right? The cofactor is going to be I, J, K, right? Front row dotted with the cofactor vector along the front row. And because we're deleting the front row and these are row 2 and row 3 of A, then we just need to write in what our cofactor vector was before. So 1, 1, minus 1. Okay? If you don't follow the reasoning, you can comment on the video and ask. I might be able to explain it a bit better. But the punchline, I guess, is that this matrix looks exactly like A except for the front row. But if we're going to find the determinant by taking cofactors along the front row, then we're deleting the front row anyway. So I can just use the cofactor vector that we found for A, because that only cares about the second and third row, which are the same. Alright? Sorry if that one's confusing. And so we got I times 1 plus J times 1 minus K. The minus 1 there. And this will give us sorry now. This will give us I times 1, which is E1 times 1. I get a 1 in the front row. Plus J times 1, so I get 1 in the second thing. J is E2. Minus K, which is E3 times 1, so I get a minus 1 down here. And wow, this is just the cofactor vector. Okay, so that's, funny. And now remember, we just did R2 cross R3, and we need to dot in R1. So 1, 2, 1 dotted with what we just found. So R1 dot R2 cross R3 going to be 1, 2, 1 dotted with R2 cross R3, which we found to be 1, 1, minus 1 for the cofactor vector. But we already did this. We know if we dot the front row of A with the cofactor vector along the front row, that this is just going to give us the determinant. Okay, and if we actually calculate it, we know it's 2. Right, you can do that. 1 times 1 minus 1 here, and know that all that's left is 2 times 1. So, again, the punchline of the question is that you can find the determinant of A also by doing this. There are many ways of finding the determinant. Okay? In particular, our cofactor expansion is the one you use the most. You can also do this. There's also other ways, right? You can find the determinant by doing row reduction and knowing certain rules there. We'll come to that a little bit later. Now, part E, this might take us a while. We need to find the cofactor matrix, C. Now I'm going to write A out again, and we're going to have some fun trying to do this. The good thing is I already know the first row of B, 1, 1, minus 1, and we just need to fill in the rest. Okay, so I'm going to do the second row in green. C2, 1. We know that it's going to be minus 1 to the 2 plus 1 times the subdeterminant when I delete the row. What do I delete specifically? Well, C21 tells me go to the second row, first column. So here, I'm going to delete this and this. And now I need to take the determinant of what's left. So 2 times 1. 2 times 1 minus 1 times 0. It's going to be minus 1 cubed into minus 1 times 2. So I get minus 2. Next guy, C2, 2. So minus 1 to the 2 plus 2. Playing here now. Go to the second row, second column, right here. Delete the, and now take the subdeterminant. I'm going to get 1 times 1 minus 1 times 1. And it comes out to be 0, because I have a 1 minus 1 inside here. Alright, not bad. And finally, C2, 3. It would be minus 1 to the 2 plus 3. And that means go to the second row, third column here. That means delete D, that. Apology for the messiness. But now the subdeterminant would be 1 times 0 minus 2 times 1. No, this is minus 1 to the 5. It's actually a minus 1. And now inside here I have a minus 2. And this comes out to be plus 2. Okay? So hopefully you're seeing what's happening here, right? Sorry about just mixing all the colors. But for this guy here, I'm using blue, right, when I deleted the row in the column. Which means take the determinant of everything that's not been crossed out by blue. And that's this guy, this guy, this guy. Alright? And now this is a 2 by 2 matrix, so I can take the determinant between 1 times 0 minus 2 times 1. Okay? This shape again. Woo. Alright, remember this shape for 2 by 2 determinant. I'm gonna write out A again, because I just made it into a mess of scribbles. And now we're gonna guess cofactor expansion along the third row. Okay, so we're going to be looking for D31, D32, and D33. I guess I'll do this in blue. Actually, no. I'm going to go with orange. D31 is minus 1 to the 3 plus 1. Now inside, I go to the third row, first column here. I delete this, I delete this. And now I take this determinant, 2 times 1 minus 1 times 1. Okay? Delete these. So 2 times 1 minus 1 times 1. Minus 1 to the 4 is plus 1. Talked about that before. It's 2 minus 1 squared, which are both plus 1. And now inside here I have 2 minus 1 is 1, so this actually just turned out to be 1. C3, 2, going to be minus 1 to 3 plus 2. I go to the third row, second column here, I delete D, 1 times 1 minus 1 times 0. comes out to be -1 to the 5 and -1. And inside the bracket here I just have 1, so this comes out to be -1. And finally, the last guy, -1 to the 3 plus 3, and going to be delete this guy and this guy and take this determinant. So we get 1 times 1 minus 2 times 0. -1 to the 6 is +1, and inside here we have +1. That would be +1. Okay, finally. Alright, we've found all of them. So let's write out what our matrix C actually is. Alright, we knew the first row was 1, 1, -1. See here, the third row is going to be 1, -1, 1. And the second row will be -2, 0, 2. -2, 0, 2. Okay? We'll be proud. That's the right answer. We did all that work. Okay? We're about to use this. So part F now wants us to compute the matrix product AC transpose, where C transpose is the transpose of C. Okay? So before we move on to this question, I'm going to write down what the transpose of C is. So hopefully you're grand with transposes, because they are grand. So a transpose leaves the diagonal alone, and then it flips everything along the diagonal. Okay? So imagine I leave the diagonal alone, and then I flip everything around the diagonal like this. So, you'll see what I mean now. So -1, or 1 here and -2 swap, right? They flip along the diagonal. So I end up with a 1 here and a -2 here. Again, same thing here. -1 and 2 flip along the diagonal. So I'll have a 2 here now and a -1 here. Of course, -1 up here is going to flip along the diagonal to here. And same as 1 is going to flip along the diagonal to here. I have a -1 down here and a +1 here. Okay? So that's C transpose. And now I want to multiply A by C transpose. So A C transpose is going to be 1, 2, 1, 0, 1, 1, 1, 0, -1. And I really want you to pay close attention now, because you need to know how to do matrix multiplication. Okay? There should be no confusion about this. Everyone in this module, at the bare minimum, why you should learn how to multiply 3 by 3 matrices. If you're an engineer, you will have to do this. You will have to take determinants. You will have to take cross products. I know you will. This is the time to get it right. This is the time to practice, right? Not in third year when you've got a fluid mechanics module and you've forgotten how to take the determinant or find eigenvalue or whatever, okay? Get good at matrix multiplication now. Get good at determinants now. So, if we multiply this out directly, in Klaus's solutions for this, he doesn't multiply them out directly. Okay, he does A times columns and calculates it like that. I'm not going to do that because I know he can just multiply these out. So, the first entry up here in the top left is going to be the first row times the first column. Okay, this is the first row of the first. Alright, this here is in the first row in the first column. So we do row by column. This. So I'm going to get 1. Alright, I'm going to leave in these lines because they're helpful. So I get 1 times 1 1 plus 2 times 1 is 2 plus 1 times minus 1 is minus 1. Okay, that's our top left entry. Cool? So then we want to do this bit here, which is in the first row but the second column. So I do first row times second column. 1 times minus 2 is minus 2. 2 times 0 is 0. And 1 times 2 is 2. Plus 2. Alright? And finally, this entry here in the first row and the third column. So multiply the first row by the third column. 1 times 1, 1. 2 times minus 1 is minus 2. And 1 times 1, plus 1. Alright, we found the first row of our matrix. Not bad, not too difficult. Alright, a really loud motorbike outside. I'd say your man riding it actually has a massive penis. So, on to the second row now. Never fucking rev your motorbike outside my house again. Okay. So, we're on this guy here, which is in the second row in the first column. You know the story by now. Second row, first column. Alright, I get 0 times 1 is 0. 1 times 1 is 1. And 1 times minus 1 is minus 1. Now here, second row, second column, second row, second column. Alright, I'm going to stop drawing these lines now. Hopefully you get the idea. If you want me to do another matrix multiplication where I go through it more carefully, let me know. So, I get 0 times 2 is 0. I get 1 times 0 is 0. And then I get 1 times 2 is 2. No, I just have 2 here. And finally, here is the second row, third column. So, second row here, third column here. 0 times 1 is 0. 1 times minus 1 is minus 1. And 1 times 1 is 1. Okay? If you're still confused about what's happening, hopefully not. But when I'm multiplying a row by a column, I'm thinking of rotating the row here, right? So if I'm calculating this entry here, the third row, first column. Third row times first column means rotate this row here up to 1, 0, 1, and then take the dot product with the first column here. So 1 times 1, 1. 0 times 1 is 0, and 1 times minus 1, minus 1. Third row, second column will give me minus 2, 0, plus 2. And third row, third column will give me plus 1, plus 0, plus another 1 there. Alright, we've done it. Usually when you do 3 by 3 matrix multiplication, there are more zeros, so you don't have to do a load of work for each entry. You know, a lot more stuff disappears. But this question is trying to illustrate a point, so you'll soon see the point. 1 plus 2 minus 1 is 2. Minus 2 plus 2 is 0. 1 plus 1 is 2. Minus 2 is 0. We get a 0 here, 2 here, another 0 here, then a 0 here, a 0 here, and a 2 here. And hopefully somebody recognized what was happening here. So this is precisely mechanically equal to the determinant of A times the identity matrix in 3D, in OR3 I mean. So remember, the determinant of A was 2, and the identity matrix looked like 1, 1, 1, 0 everywhere else. And this is always true. So what we did was we multiplied A times the cofactor matrix of A transposed. And if you take any matrix and multiply it by its cofactor matrix transposed, you will always get the determinant of A times the identity. Okay? Not bad. So, part G, then use your answer to F to compute A inverse. And so I'm going to do this in red because it's something you should know, right? If the determinant of A is not equal to 0, then A inverse exists and is given by A inverse equals 1 over the determinant of A times C transpose. Where the hell did this come from? It's actually not too bad to see. So we did in the previous question A times C transpose, and that gave us det A times the identity. So you can see if I apply A inverse to both sides, I'm going to get A inverse A C transpose equals the determinant of A is just a number, so I could bring it to the front when I apply A inverse. Now, A inverse times A is the identity. And here, A inverse times the identity is just literally A inverse, because the identity doesn't do anything. When I multiply something by the identity, nothing happens, right? It's like multiplying by 1. So the identity times C transpose is just C transpose, like that. Det A times A inverse. And the last step now, of course, to find A inverse, we need to divide by the determinant of A on both sides. So C transpose divided by the determinant of A equal to A inverse. Okay, so this is just a small derivation. You don't need to remember this, it's just where this formula comes from. Now, maybe alarm bells are ringing when you see this thing here. You know, you might think we're dividing matrices. Remember, the determinant of anything is a number. The determinant is never a matrix. So I'm perfectly fine to divide a matrix by a number. Okay? I just divide each entry of the matrix by that. So let's actually calculate what this is. A inverse is going to be 1 over the determinant, which is 2, times C transpose. We found C transpose to be 1 minus 2, 1, 1, 0, minus 1, and minus 1. Alright, minus 1, 2, 1. Yes. And you can leave it like this, or you can bring in the factor of a half. So I got a half there, minus 1 here, half here, a half, 0, minus a half, 1, half. Alright, not bad at all. Here's the inverse of A, and in general, the inverse of a matrix is going to have fractions in it. Usually these fractions are much mankier. It's actually a good thing that in the question we only end up with fractions of a half in our inverse. Okay, so we're getting there now, right? There's only 3 more parts. 4. So H, since A is invertible, we know that A reduced into the identity matrix. Okay, I just want to highlight this sentence. You can show any matrix is invertible by showing it row reduced into the identity matrix. Okay, you can also show that if A reduced into the identity matrix, that it's invertible. Okay, saying A is invertible, it's the same thing as saying that A row reduced into the identity. Okay, they mean the exact same thing. Now, question is, does this mean that the determinant of A is the same as the determinant of I? Well, this can't be true. Right, we know for a fact that the determinant of A is 2. And if you didn't know, the determinant of I, the identity, if you were to do cofactor expansion, you can see you get 0 up here, so it comes out really easily. The determinant of the identity is always 1. So they're definitely different. Now, why are they different? Well, there's a few things. When you're row reducing, right? So if you add / subtract rows / columns when row reducing, the determinant doesn't change. The determinant doesn't change. So remember, when we're doing row reduction, if I take my first row, let's say, and I subtract the third row from it, and I get a new matrix, the determinant doesn't change, right? The determinant of both of those matrices will be the same. That's fine. That doesn't explain what's going on here. But now the second thing, if you swap rows or columns, then the determinant is multiplied by -1. Multiplied by -1. Okay? So if I were to take my matrix and I'm doing a row reduction and I swap the first and the third rows, the difference in the determinant between those two matrices before I swap and after I swap is going to be a factor of -1. So that explains some of it. And finally, if you multiply a row or column by some number k, right, like a half or 5 or 3 or any number, if you multiply or divide, then determinant is also multiplied by k. So if I had my matrix and I multiplied the first row by a half, then the difference in the determinants of those two matrices before I multiply by a half and after I multiply by a half is literally going to be a half, right? The determinant after you multiply by a half of the original determinant. So this explains why when we row reduce A to the identity that the determinants become different. At some point when we were row reducing, we probably multiplied by a factor of a half, which is why the determinant went from 2 to 1. And we're going to see some of this now, and it's important to know, because this is another way to find the determinant if you want to. You can take your matrix, reduce it to the identity, keep track of all the little steps you do there, right? When you swap column, when you swap row, when you multiply row by number, and keep track of what's happening to the determinant. And then you know that the determinant of the identity is 1, so you can work backwards through all the steps you made to row reduce this and find the determinant of A. And this is how some computer programs actually do find the determinant, because row reducing is really efficient on a computer. So calculating the determinant like that is also pretty efficient. Okay, part I. Hint A, when we do the operation of minusing R1 from R3, we should expect that the determinant of A is the same as the determinant after we do this. Verify this. Okay. Verify it. So A1 is 1, 2, 1, 0, 1, 1, 0, minus 2, 0. And now I'm going to do this quickly. Okay? This is how you get a determinant quickly. I'm not going to do slow cofactor expansion and then dot producting them. I'm just going to do it all together at once. So the determinant of A. Whoops. Sorry. This notation here, 2 vertical lines, it's sometimes used to note the determinant. So the determinant of A is going to be now. I take my first row here, and I'm going to do cofactor expansion along the first column instead of row. Because the first column had 2 zeros in it, it's way easier to calculate. Okay? Because 0 here and 0 here mean that I'm going to get zeros in the cofactor expansion if I were to do it. So what this looks like is I start with 1, top left, I delete this row, this column, and I take the subdeterminant here. And I multiply it all by 1. So I get 1 multiplied by 1 times 0 is 0, minus 1 times 2 is plus 2. So I get that. Now the second thing I need to do is take 0, delete this column, this row, and take the subdeterminant. But when I do this, I'm going to be getting 0 multiplied by this determinant, 2 times 0 minus 1 times 2. It doesn't really matter what I put in here, right? It doesn't matter what that subdeterminant is, because it's on the outside is multiplied by 0. Similarly with the third column here, if I delete this row and this column, take the determinant, it doesn't really matter. I have a 0 on the outside. Okay? So this determinant ends up just being 1 times 2, which is 2. Minus 0 plus 0. And, I mean, that's the end of the question. So I know I did this lightning speed. If you want me to do this in detail, you want me to explain a bit more about why being 0 make everything disappear, again, you can just comment. Comment on the video. I'll try and explain it a bit better. Part J now. A1, this is a new, sorry, A1 now, we're going to then do R3 and multiply it by minus a half. We should expect the determinant of A2 to be minus a half of the determinant of A1. Okay. Well, the good thing here is that we can roughly do what we did before. And calculate the determinant by doing cofactor expansion along the first column. Because there are 2 zeros in it. Make it easy. So I'm going to get the determinant of A2 to be minus 1 to the 1 plus 1, which is 1. And then I multiply 1 times this subdeterminant. 1 times 0 minus 1 times 1. Second cofactor expansion is 0 in front of everything. Third cofactor expansion is 0 in front of everything. And so the determinant of this ends up being minus 1, which is the same as minus 1 half times 2, which which is exactly minus a half times the determinant of A1. So the determinant of A2 is minus a half times the determinant of A1, which is what we needed to show. Am I going too quick? Probably. Part K now. Last part. So how are the determinant of A and 2 times A related? Explain. Now, if you're naive, you might think that, alright, if I multiply the matrix by 2 and I get the determinant, then surely I just multiplied the determinant by 2 as well. Okay? It's wrong. Not true. Okay? Don't do that. The reason why it's wrong is if we take A, so 1, 2, 1, 0, 1, 1, 1, 0, minus 1. Sorry. Then A. And now 2A is going to be 2, 4, 2. 0, 2, 2. 2, 0, 2. So maybe already you see why this guy is wrong. Because now, so now what I'm going to realize is when I take the determinant of the 2A, because I've multiplied every entry by 2, when I do the cofactor expansion, I'm getting a factor of 2 in every subdeterminant. Yes. So I'm getting an extra factor of 2, right, when I multiply this 2 by this submatrix. Okay? So I'm picking up a factor of 2 here, another factor of 2 here, and another factor of 2 here. So every time I find a subdeterminant and I dot it with the cofactor vector, I'm getting 3 factors of 2 because it's a 3 by 3 matrix. So the rule is actually that the determinant of A is going to be 2 to the power of 3 times the determinant of 2A. Okay, I get 3 different extra factors of 2 because I've put an extra factor of 2 in every single entry when I multiply it by 2. And 2 cubed is 8. Okay? You can also view this, if we go up now, and we check the rule. Okay? If I multiply a row or column by k, then the determinant is also multiplied by k. Well, if I multiply the entire matrix by k, okay, then I've multiplied 3 rows and columns by k. So obviously if I take the determinant of that, I'm going to get 3 different factors of k in the determinant. So of course I'll get k cubed times the determinant. Alright? So in general, if A is an n by n matrix, then the determinant of A sorry, I got something very wrong here. This should be the determinant of A. This over here should be 2A. Sorry. Okay. So I have to raise up the determinant of A by multiplying it by 2 cubed to get it to be the determinant of 2A, because the determinant of 2A is obviously bigger than the determinant of A. Alright, so if A is an n by n matrix, then if I multiply a by a constant lambda, I relate the determinant by putting a lambda to the power of n in front of the determinant of a. Okay, so this should make sense just by thinking about the fact that when I multiply a matrix by lambda, I'm getting an extra factor of lambda in every single entry, every single one. So then when I take the determinant, I'm going to get extra factors of lambda n times if it's an n by n matrix. Okay? That is the end of this problem set. I know it's long, or I know it's arduous. I know the determinant calculations are pretty annoying, but practice is the key. Okay? So please practice them. You know, you're probably gonna get a determinant on your final exam. You know, I can't promise you that. I don't even know, but it's something really important that you should know how to calculate. So please learn how to do it. Alright. I'll talk to you soon, and hopefully I have everything corrected.